Please, the floor is yours.
Yeah, hello everyone. Thanks a lot to the speakers for organizing this nice meeting and inviting me. I was kind of thinking I'm a little bit of an outlier working on ultra-cold gases, but then I talked to some other people who also felt like they were the outlier. So maybe none of us are outliers and we just have a very broad conference. So having said that, I will try to give a broad introduction into this kind of field and the reasons I'm interested in it, and then I will get to the actual results, which is, as I said, about spectroscopy of trimers and polarons in ultracold mixtures. So generally speaking, I think one question which I find very interesting is how we can study chemistry in a medium, really from a bottom-up perspective. So of course, many people in the audience like doing molecular spectroscopy, which is the aim to understand very well individual molecules by studying them in their gas phase, isolating them, and then really very nicely studying their properties. The question is, can we do a similar approach to study chemistry in a medium? And this is by definition very hard because the medium is often complicated and introduces a lot of broadening and mess into the problem. And for example, one very nice example where they do this is by immersing molecules in helium droplets, which perform a nice kind of medium which doesn't hinder the molecules too strongly and still forms kind of a nice environment. And we will hear more about this tomorrow, I think. But still, helium is still very hard actually for a theorist to really describe the whole many-body dynamics in this helium droplet. So I want to advocate for even a simpler system maybe, which is even still in the gas phase. So the question we can ask, can we use a gas phase experiment to really study still in medium effects? This sounds like a contradiction, because a gas is not really like a medium, right? I mean, all the atoms are kind of isolated, and if I would put one more atom in my gas, the rest of the particles would barely notice. It would not really deform, and therefore there no effect like solvation or something like that. However, this is at normal temperatures we're all used to. And at normal temperatures, the de Broglie wavelength of the atoms in the gas is very short compared to the interparticle distance. But in principle, there's no fundamental reason for this to be the case, right? So if we just cool the gas down by a lot, then also the de Broglie wavelengths of the atoms in the gas will start to overlap. So you need to go to microkelvins or nanokelvin regime to get to this, but we have mastered this. In experiments, they can do this now. And in fact, in this regime, the particles in the gas start to behave a little bit even like electrons in a solid, for which the wave functions already overlap at room temperature. Right? So now we can really start to see medium effects in this ultracold gas. And one very nice, simplest example is by just comparing what happened to different isotopes of the same atom. Right? So if you have 6 lithium or 7 lithium, in all chemical senses it will probably behave almost the same. But if you cool now this gas down to very cold temperatures, you will see that the fermions obey the Pauli principle. So if you have a harmonic trap for your atoms, this means that only one fermion can occupy every level with the same spin. Whereas for bosons, all the particles can go into the lowest level of the trap. Therefore, if you cool down the system cold enough, here, 240 nanokelvins, right, we see that the fermionic lithium forms a degenerate Fermi gas, and the bosonic lithium atoms form a boson-Einstein condensate, which was a phase which was sought after in condensed matter physics already since midway the previous century, but which was realized first with ultracold atoms. And now this boson-Einstein condensate is actually the ideal medium for the purpose of this talk. Because to write down the wave function of this thing as a theorist is incredibly simple. It's just all the particles are exactly in the same quantum state, which is the ground state of this trap. This is the ideal world for a theorist. Of course, now we can ask, is there actually still some interesting chemistry going on? The first thing in which I also want to tell you is that we do actually get something which I like to call solvation. And by solvation I mean is that the background gas kind of adjusts itself to the presence of some kind of impurity. Right? So if I insert now an impurity atom of a different kind, which interacts with the atoms in the background BEC, we will see that the BEC locally deforms itself around this impurity. Yeah, it can either increase its density locally if the interaction is attractive, or you can get a reduction of density if the interaction is repulsive. And this is a little bit similar to an impurity in a fluid, which also locally rearranges the particles in the background solvent. However, it's also quite similar to a well-known case of condensed matter physics. My clicker is not. Which is impurity in a crystal. because in an electron, for example, in a crystal also locally deforms the surrounding crystal, or you can view it as being dressed by quasi-particle excitations, which are called phonons, which are bosonic excitations. And it turns out this electron can now be described by a so-called quasi-particle in quantum metaphysics, which is called a polaron. And this polaron behaves as a kind of new particle with different properties. So now our impurity in this ultracold gas, we can also view it in this polaron picture, where really it behaves now as a kind of a different particle with slightly different properties, while at the same time, we also have actual atoms in our system. And these atoms, they can form bound states, they can form molecules, and therefore there's also some connection to chemistry. So I think this is a really nice platform to kind of study the interplay between the effects of these kind of different fields. So before I move on, I want to tell you also a bit more about the interactions which you have in these ultracold gases, which you can view as scattering processes. But what is very interesting at these ultracold temperatures is that the wavelengths of the particles become much, much longer than the interaction, the range of the interaction potential. Yeah, so the interactions between these neutral atoms are set by the van der Waals interaction, right? And they have a typical range of about 58 knots. So this is a typical length scale you can associate with these interactions. However, the wavelength of our ultracold collisions can be thousands of Bohr radii, which means if you look at just the scattering wave function, right, as a function of the interparticle distance, the wavelength is very long compared to this tiny area where you actually have the potential. And this means also that our wave function doesn't fully really resolve all the details of the potential. And the only thing which can really happen during this collision is a phase shift. Okay? So all we need to know to fully characterize the scattering is this phase shift and how it depends on energy. And it turns out there's a very simple universal formula which applies in this regime, where like k times the cotangent of this phase shift is just given by this -1/a, which is called the scattering length, plus some corrections at higher momenta. And usually for most ultracold gases, only this a parameter is enough to kind of fully describe all the relevant properties of the collision. And in fact, if this a is 0, it is as if the atoms were non-interacting, right? Because it's almost as if there's no phase shift after the collision. If a goes to infinity, then the peak of the wave function is at the at interparticle distance 0. So this is when you have the strongest interactions, and a negative scattering length is felt as an effective attraction, and a positive scattering length is felt as an attractive repulsion. So now we can understand kind of the interactions with this very simple picture. We don't even need to know very well exactly what is the detailed interaction potential. We only need to know these very few universal parameters to describe our many-body system. What is even more nice is that the scattering length can even be tuned. And this we can do using scattering resonances. So you can imagine that the atoms, when they're far away, they're all in their internal ground state, so their ground spin state. But of course, the atoms do have multiple spin states, and when the atoms collide, they can start to also temporarily populate higher spin states. And in these higher spin states, there can be a bound state. And if this bound state is then brought into resonance with the collision energy, the particles can temporarily kind of get trapped there before they go back out. And this increases the effective interaction strength. And in fact, when this bound state is exactly on resonance with the collision energy, this scattering length parameter diverges, right? But what is now very nice is that since these channels correspond to different spin states, we can tune their relative energy with the magnetic field. So this means that the position of this bound state compared to the threshold can be tuned magnetically. So this means that by just changing the magnetic field, so this is the scattering length as function of magnetic field, you can even tune this effective interaction strength from -infinity to infinity. So what more would you want? You see here you have these kind of resonance patterns. And here you also see plotted the binding energy of these resonance states and how they go into the continuum. So now I just talked about tuning the interactions between atoms, but I promised you molecules. But in principle, if now this bound state, this kind of virtual resonance state, is brought to be below the scattering threshold, then we actually have very weakly bound molecules. And by, for example, adiabatically changing the magnetic field, you can turn these atoms which are temporarily trapped in this resonance state into really bound molecules. And these are the kind of molecules I'm going to be talking about today. So they're molecules in the highest vibrational state of the intermolecular potential. So real chemists would probably not really call them molecules, But keep in mind is that also the energy scale of our medium we're talking about is also 100 nanokelvin or a microkelvin. So to get the most interesting interplay between our solvation process and our binding process, we want them to be on the same energy scale. So to get interesting physics in this very ultra-cold sample, we also need to look at extremely weakly bound molecules. One more thing I want to say is that you can also make these molecules spectroscopically. So you can start with an initial spin state where there's no molecular state weakly bound, and then transfer one particle to a different spin state where you can go kind of from this continuum into one of these molecule states. But why would we even stop at 2 particles? We can also get molecules of even more particles. And in fact, bosons even like to form molecules of more particles. So if you plot here the molecular states which appear in your spectrum, you see that already, this is the inverse scattering length, and you see this dimer state appears when the scattering length diverges, but already before the dimer state appears in the spectrum, actually even an infinite number of trimer states appears. And this is a kind of cooperative binding, because if I remove one of these particles, then also 2 other particles will go away. And what's interesting about this is a pure quantum effect, because if I have 3 particles just interacting with pairwise potentials, classically there's always a bound state in this pairwise potential. You can always just sit at this bottom of this well. However, quantum mechanically we have this concept called the 0-point energy, which means a bound state does not always fit. So this way it can happen that in a single pairwise potential no bound state fits, but if then 3 particles come together, then you can get these bound states. All right. So this was for 3 identical particles, but I was interested in this impurity scenario where we have 1 different particle immersed in this kind of solvent. And then this effect can either be enhanced or suppressed depending on the mass of this other particle. And it turns out that this effect is enhanced if you have a light particle, because it then can efficiently move between the particles of the solvent, and it gets suppressed if you have a heavy particle, because then it just acts as some kind of external potential. And if you just have 2 particles in external potential, the binding energy of the trimer is just twice the binding energy of the dimer, and you don't see any of these interesting effects. And even the interboson interactions can also be different, and this also plays a big role, as you will see. So now we've kind of set the stage. So now we have our molecular states, our dimers and trimers, for example, which we are interested in, and we have our medium. And now we can ask, what is now the interplay between the formation of these molecular states, of dimer states and trimer states, but now in this kind of quantum solvent? Yeah, and this I like to call chemistry in a quantum medium, because we really now start to see how this medium effects, this polaron physics, start to affect the formation of these bound states. And we wrote a couple of theory papers about this over the past years, so you're very welcome to check this out. Today I want to talk about some results together with the experimental collaboration of the group of Martin Zwierlein. So first I will talk to you about the direct observation of these kind of very weakly bound trimers in the system, in a regime which was not really observed before. And then I will talk to you how this changes if you put it in this degenerate Bose-Einstein condensate, and we'll see the very exotic phenomenon of not just having a dimer or a trimer, but even a superposition of a dimer and a trimer in this special medium. So let's start with this. Yeah, so this was work together. The experimental work was all done in a group of Martin Zwierlein, who is at MIT, and is excellent students. And in theory, I work together with Denise, who's a postdoc in Antwerp. So what do they do experimentally? So they create a gas of sodium, which is now above the critical temperature for condensation, but only like a factor 1.5, and they have some potassium impurities. So they start at relatively strong attractive interactions, but where there's no bound state yet, and this is done to enhance the kind of the wave function overlap with these bound states if you want to create them spectroscopically. And what they then do is they do a Raman transition or a radio frequency transition to a different spin state of this impurity atom to transfer it to the state without the bound state to the state with the bound state. And then they can measure the number of atoms which were removed from the initial spin state as a measure of kind of the response. So the kind of spectra what they were used to see is a little bit like this. So you have one big peak, which corresponds to just the transition from a free atom to a free atom, but a bit detuned from that, you see a peak of a dimer where you have associated the particle into this kind of bound state. But now instead of only this dimer state, in the new spectra, we see a very clear double feature of both a dimer state and a trimer state appearing. And it turns out that, so the bare atomic transition would be somewhere here, right? So it turns out that compared to this dimer, the trimer is very weakly bound. However, it's not kind of just a fluke at very one special magnetic field, because they see over a whole range of magnetic fields and over a whole range of dimer energies, they see that this trimer state persists and that it's kind of always weakly bound. So you might ask, are you really sure this is a trimer state and not just another type of dimer? And what we can do is we can measure not only the number of potassium which was transferred, but also the number of sodiums which get lost. Because these trimers are not very stable. They are in the highest possible vibrational state. So if you have 3 particles together, they can also find a way to relax to these lower vibrational states. And then one atom is kind of emitted away. And we see that if we create one of these trimer states, per potassium atom which is transferred, 2 sodium atoms are lost, which means that we really have 2 sodium per potassium. Whereas if we create a dimer state, the dimers themselves are stable, but if they collide with one more particle, it also gets lost. But then it can collide either with the sodium or with the potassium, and this means that you get some ratio in between 1 and 2. So we clearly see that these 2 peaks have a different nature. Finally, if you go very close to the resonance, also the dimer state can directly be detected, whereas the trimer state is too short-lived for that. Okay. So how do we model this theoretically? So actually, if you want to compute this trimer energy using fully the up initio potentials, with all the bound states in there, and also the internal spin structure, is extremely hard and extremely challenging. However, we don't really need to do this, because these trimers are so weakly bound compared to the range of this potential that we're still in this kind of universal regime. And this means that we can take some effective potential, which just has the same low energy scattering properties, and this should then still probably give the same trimer energies. And for the dimer, we know this works, because the dimer energy, which is shown here with this blue and red dots, follow a very nice universal energy dependence, which only depends on this A and this RE here, right? And we see the solid line is just effective range model, and it agrees almost perfectly with the experimental results. So what we do now is just have simple model potentials with these same parameters as the real potentials, and then we can compute this trimer energy much simpler. We are still investigating also the effects of these different spin states, including that, and more bound states, but this is still ongoing work. So what we see here is the blue dots are the dimer energies measured in experiment, and the red triangles are the trimer energies, and we see we get a very good agreement already with the simple model. But if we look a bit closer at the actual difference between the dimer and trimer, which is the most interesting parameter, we do see some systematic deviation. So here the dots are the experimental results, and the error bars are just the statistical error bars from their fits, but more realistic error bars, the green shaded area, which is more the width of their line in general. Because they have all kinds of saturation and heating effects going on, it's very hard to actually really pin down very well this trimer energy. And we see that the theory, the trend agrees very well, but we're not completely sure yet what's the origin of this deviation, whether it's something on the theory side or the experimental side. So what do these trimers really look like? Well, it turns out that they have a very simple structure, because the trimer is only very weakly additionally bound to the dimer. We just have one tightly bound dimer state with the third particle being relatively far away, right? So here you see the distances of the between the 2 bosons and our impurity atom, and we see that one particle is always pretty close, whereas the other one that is much more extended, right? So if you have one axis is only half of this A, and the other direction is much more extended. And even a very simple wave function of this form, where we just take one particle in the dimer wave function and one particle in an atom dimer wave function, which we construct, plus the symmetric superposition, turns out to have a good overlap with the full trimer wave function up to 98%. So we can have a very simple model of what this trimer actually looks like. I want to say one more thing is about how you actually need to extract the trimer energy and dimer energy from the experiment, because the trimer energy is not actually at the top of this peak, nor is the dimer energy. And that's because they have a non-trivial line shape. So for example, the dimer has a very discrete binding energy, but the initial atoms, they have also some initial scattering energy. So this means you don't only need to when you transfer the free particles to the dimer, you don't only need to compensate for going from zero energy to the dimer, but you also need to take account this kind of thermal energy. This means if this is your dimer energy, you always have a line shape which is asymmetric to lower energies. For the trimer, that is similar, it's only that the energy scaling is a bit different, and I don't want to go into detail here. Okay, anyway, so this is important if you actually want to pin down this trimer and dimer energies. So experimental spectra don't look so asymmetric, but that's because they have other broadening effects which are of similar order of magnitude as this thermal broadening. There's one small mystery which still remains, is that why is this trimer so strong? Because it's almost equally high as this dimer peak, whereas theoretically we would only expect that the trimer is like 20% as high. And we're still trying to figure out what this actually is. Alright, so now I've shown you that we have these dimer states and trimer states, which both appear in these ultracold gases. And now I'm going to tell you how this experiment behaves if we repeat it exactly, but now in a degenerate Bose-Einstein condensate instead of in a thermal gas. And this was again experiments done in the group of Martin Zwieline, and the theory was together with my PhD supervisor, Richard Schmidt. So what I show here is they have kind of a harmonic trap, which is elliptical, in which you have the sodium BEC. And what they can very nicely do now is to resolve their spectrum as a function of the position in this cloud. Okay? So at the edges they have very low density, whereas in the center they have very high density. And otherwise the experiment is kind of the same. So they see at the edges they have very narrow peaks, corresponding just to the free atomic state and to the dimer and trimer state. Or trimer they don't really see here. But then we see if we go into this high density regime, we get the shift of the line and a lot of broadening. And of course, by itself, it's not surprising. If you put something in a medium, you get a shift and a broadening. Who cares? However, so it does show that there are clear medium effects. However, we can nicely understand this using a very simple theoretical model. So now we take a wave function, which is not just a dimer or a trimer, but it can be a superposition of a free impurity, a free dimer, and a free trimer state. And we can now see how basically a free impurity can coherently draw a particle from the BEC to go from this free impurity state to the dimer state, and the dimer can coherently draw a particle from the BEC to go to this trimer state. This way you can kind of construct this effective three-level model. If we now compute the eigenstates of this three-level model as a function of the density, we see here we have the bare dimer and the bare trimer, but the coupling with the BEC is actually stronger than this splitting. And this means if you just look at this Hamiltonian, that these levels very strongly hybridize and have a very strong level repulsion. And the colors here indicate the nature of these eigenstates, and you see that there are very clearly mixed states between the dimers and trimers. So really we don't have just a dimer or a trimer anymore, but yeah, a coherent superposition of them. And if I plot these lines together with the experiment, I get these solid lines here. So this is without any fitting parameters to the experiment, so purely based on the theory models. And I have to say this lower line is supposed to capture the belly of the spectrum, because it's the minimal energy of a variational calculation. And the other two lines are a bit more phenomenological. So we see the lower line captures reasonably well the bottom of the spectrum, not 100%, which is also my trimer energy was not completely accurate. There are other sources of broadening. Maybe I should go beyond this three-level model, but at least qualitatively it captures it. And also the total splitting between this dimer and trimer energies also nicely captures the width of this feature, really showing that this dimer-trimer hybridization is very important. For reference, if I had not included the trimer state in this model, I would have only gotten this dashed line here, which clearly does not capture, the extent of this belly. So it turns out really this dimer-trimer mixing is super important to explain the experiment. And this is really, I think, a very nice example of how molecule formation and how molecules are very different inside this degenerate medium. Okay. So finally, this is not just for one magnetic field, we can also do this as a function of magnetic field. And we see this nicely follows this dimer energy curve, which we saw before, but now including this wide broadening. And the theory lines capture relatively well the experiment over this whole extent. So with that, I want to conclude. So I've shown you today the formation of these very weakly bound trimers, aside from just the dimers, and how the dimers and trimers get hybridized in the medium. As one teaser, this is of course not the only chemistry you can do on ultracold systems. As Etienne was talking about, you can also have ultracold molecules in their ground state, and when they collide, you get all kinds of mess, which can happen, real chemical reactions going on, also in presence and photoexcitation reactions. So I've also worked a lot on this. If you're interested in that, please also talk to me. And with that, thanks for your attention. I'm happy to take any questions.
Okay, so the talk is open for questions. Someone? Nobody have any questions?
What happens with still? Why does it stop with interaction with tree?
Yeah, that's a very good question. So in this case, if there were no interactions between the bosons, we would have gotten a trimer energy which is below twice the dimer energy. So it's really the repulsion between the bosons which makes this thing weakly bound. So we think in this case that the tetramer state would be just even more weakly bound, if it even exists. It's not clear at this point whether it exists. In general, though, if you have this original Efimov scenario, where you have this three-body bound states of identical particles, then it's always more favorable to have more particles. So then you really can get larger and larger clusters. But this really depends on the interactions inside this medium.
Okay.
Right.
Other questions? Okay, if not,
All right.
thank you very much for your talk.